Hello everyone, this is lecture 22 of the subject analog circuits. In this class I am going to discuss differential amplifier. Contents are, firstly I will discuss the basics of differential amplifier, and after that MOS differential pair, then small signal operation of MOS differential pair, and common mode gain and common mode rejection ratio for differential amplifier. Now, before starting the differential amplifier, let us review that how many amplifiers we have studied till now. In unit 1, we had designed amplifier using BJT and using MOSFET. There we had designed the amplifier in common emitter configuration or in MOSFET common source, and we prefer this common emitter and common source when we need voltage amplifier because of the higher input resistance of this common emitter and common source amplifier. But in common emitter and common source amplifier, what we had done, we were applying the input signal at a single terminal, right. For example, if we consider the common source amplifier using resistive load, then there we had applied the input signal at the gate of the MOSFET M1, and we take the output from the drain of the M1 transistor. This is supply voltage VDD, right. But in differential amplifier, the input signal is applied between the gate of the two MOSFETs or the base of the two BJTs. So, we can design this differential amplifier using BJT, using MOSFET. So, it is called differential amplifier because it amplifies the difference between two signals. Now, the question arises that why we are doing it, why we need to amplify the difference between two signals, because we have already this common source amplifier, common emitter amplifier using single transistor, then why we need extra transistors to apply the differential input. The reason is that, to understand it, let us consider two wires that are physically very close, fine. So, the interference or noise added to these two wires, it will be same because both are physically very close. So, if there is a differential amplifier, then it will amplify the difference between two signals. So, if the N1 noise is added to the upper wire and the N2 noise is added to the lower wire, fine, N1 and N2, and of course, this N1 is equal to N2. So, if we connect this wire to the differential amplifier, then it will amplify the difference between these two signals N1 and N2, and N1 equal to N2. So, that will be 0. So, the point is that if the noise is added, then that noise will not get amplified, that noise will not propagate it to the further stages. So, the first advantage of differential amplifier is that it minimizes, it reduces the effect of noise. Why? Because it senses the difference between two signals, and that difference between two signals means if any undesired signal, any noise or interference signal is added, then it will just cancel out that interfering signal, that noise signal at the input itself. It will not allow that noise signal to propagate to the further stages, because in op-amp design, in multi-stage amplifiers, there are many stages connected in cascade, right. We do not want any noise to propagate further, fine. So, the first stage is always a differential amplifier for any multi-stage amplifier, just to reduce the effect of noise. That is the first advantage of differential amplifier, that is noise reduction. And also this differential configuration, it enables to bias the amplifier and to couple the amplifier stages together without the need of the bypass and coupling capacitors. So, in common emitter common source amplifier we had connected bypass and coupling capacitors. Here we can avoid these capacitors, that is the very big advantage, because the coupling capacitors, bypass capacitors, it occupies a lot of area and it is impossible to fabricate such a large value of capacitors in microfarad range in IC, right. So, that is the another advantage of differential amplifier. So, one of the main advantage is the noise reduction. Now, coming to the MOS differential pair. So, once we understand the differential amplifier using MOSFET, just replace these MOSFETs with BJT. So, you can understand it using BJT also, fine. So, there are two transistors Q1 and Q2, and at the gate of Q1 transistor the voltage is Vg1, at the gate of Q2 transistor the voltage is Vg2. This current I, this is the current source that we can design using current mirror that I had discussed in last two classes. So, this current source, it bias the Q1 and Q2 transistor, it makes sure that of course, this Q1 and Q2 it should be in saturation region for MOSFET. If you are using BJT, then it should be in active region, and this RD is the drain resistance. So, here we can see that this differential structure is having passive load, because we are using resistors RD, right. So, this is the basic structure of the MOS differential pair. We use two transistors and we apply the input signal between the gate of the two transistors Q1 and Q2, and apart from these two transistors Q1 and Q2 we connect some load, either passive load or active load. We will see that the differential amplifier using passive load and using active load, one current source to bias the transistors. Now, we need to understand the working of this differential amplifier. So, we will understand it in two modes. The first mode is the common mode input voltage. What is common mode input voltage? In common mode input voltage, now we have applied the input signal. We have applied the same input signal at the gate of the Q1 and Q2 transistor, that is VCM. So, this VCM is called common mode voltage, This is, we can see that when we say that the common mode signal, that common mode signal is basically the noise signal, interference signal, that is to be rejected. Now, we will see that how this differential amplifier rejects the noise, fine. Now, see, the criteria is that Q1 and Q2 should be in saturation region and Q1 and Q2 should be matched transistors. If it is happening, then if the current is I, then the equal current will flow through Q1 and Q2 transistor. It means that I by 2 will flow through Q1 transistor and another I by 2 will flow through Q2 transistor, provided that Q1 and Q2 are in saturation region, right, and of course, matched transistor, matched. Now, see this is very clear, the gate to source voltage is Vg minus Vs, and what is Vg? Vg is VCM, that is the common mode voltage that we have applied at the gate of the transistor. Now, see, for Q1 transistor or Q2 transistor, what will be the equation, drain current equation? The drain current flowing is I by 2, because the equal current is flowing through Q1 and Q2 transistor. So, I by 2 will be equal to 1 by 2 Kn dash W by L into Vgs minus Vt whole square. This is the drain current equation in saturation region. Kn dash, that is the process transconductance parameter, W by L is the aspect ratio, Vgs minus Vt is the overdrive voltage, that is represented by VOV, fine. So, if we say this is equation 1, then what will be the value of VOV, where VOV is Vgs minus Vt. So, VOV will be under root I upon Kn dash into W by L, fine. Now, we can calculate the value of Vd1 and Vd2. What is Vd1 and Vd2? Vd1 is the drain voltage of Q1 transistor, Vd2 is the drain voltage of Q2 transistor. Now, you can see that this is supply voltage VDD, then what will be VD2? VDD minus I by 2 into RD, that will be VD2. Similarly, what will be VD1? VD1 will be VDD minus I by 2 current is flowing through RD resistor. So, what will be VD1? VD1 will be VDD minus I by 2 into RD. Now, you can see that the value of VD1 and VD2 are same, because the current flowing through Q1 and Q2 Q1 and Q2 transistors are same. So, what does it mean? It means that if we take the differential output means if we take the output between the drain of the Q1 and Q2 transistor, then the output will be 0, because VD2 minus VD1 will be 0, VD2 minus VD1 will be 0. What does it mean? It means that if any common mode signal is applied at the gate of Q1 and Q2 transistor, that common mode signal is noise signal, interference signal, then in that case the output is 0. So, that interference signal, noise signal, it is not propagating to the output. So, here we can understand that how this differential structure is rejecting the common mode signal, that noise signal and interference signal, right. So, there is an important term related to this, that is the input common mode range. Input common mode range, that in short it is called ICMR. ICMR, it is the range over which the differential pair operates properly. Properly means the all the transistors should be in saturation region and it behaves like a differential amplifier. It does not deviate from its behavior, right. So, we can find out the range of VCM, the highest value of VCM and the lowest value of VCM. The highest value of VCM is limited by the requirement that Q1 and Q2 transistor remain in saturation, that from there we can find out the highest value of VCM. To calculate the lowest value of VCM, it is determined by the need to allow for a sufficient voltage across the current source I for it to operate properly. So, to get the higher value, highest value of VCM, we will calculate that by the requirement that Q1 and Q2 are in saturation. From there we can calculate, and to calculate the lowest value of VCM, that can be determined from the voltage across the current source I, fine. So, this is an important term in differential amplifier. We consider it and we design the differential amplifier considering this parameter ICMR. Now, next one is operation with differential input voltage. Before it, I had discussed the operation with common mode signal. In common mode, the same signal is applied at the gate and Q1 and Q2, at the gate of Q1 and Q2, but in differential input voltage, now the input signal it is applied between the gate of Q1 and Q2 transistor. Now, you can see that this is ground, so it is shorted actually, fine. So, this input signal is applied, VID is applied in between the gate of Q1 and Q2 transistor. So, the remaining structure is same, fine. Now, we can understand the working. Now, see, if VID is positive, and what is this VID? VID is VGS1 minus VGS2. So, if VID is positive, it means that VGS1 is greater than VGS2. If VGS1 is greater than VGS2, then it means that drain current of Q1 transistor it will be greater than drain current of Q2 transistor. So, if ID1 is greater, then VD1 will be less, because there will be more drop across RD. So, that means that VD2 minus VD1 will be positive, because VD1 will be less. Similarly, if VID is negative, then VD2 minus VD1 will be negative. From here we can understand it. Now, see, what is the conclusion from this? The conclusion is this differential pair responds to the difference mode or differential input signals by providing a corresponding differential output signal between the two drains, right. So, what does it mean? It means that basically this differential amplifier, we are applying the input signal at the gate of Q1 and Q2, and basically we are taking the differential output. We can take the single ended output also, we will see it in further classes, right. So, this is your differential output structure, fine. So, just by whether VID is positive or negative, depending upon that, the difference between VD2 and VD1 is decided. If VID is positive, then VD2 minus VD1 is positive, right. So, this is the explanation of it. Now, see, we can derive the equation for it. Now, this is the drain current equation in saturation region. From here, let us say it is equation 1, from equation 1 we can calculate the value of VGS1, fine, and that is Vt plus under root 2 VOV. What is VOV? VOV is basically that we have already seen this VOV is under root I upon Kn dash W by L, fine. That is why we have written it Vt plus under root 2 VOV. Now, what is the VID max? What can be the maximum value of VID? The maximum value of VID, it is the value at which the complete current means I, the total current, it flows through the Q1 transistor, fine. So, in that case the VID max we are getting under root 2 VOV. From this expression we can calculate it, fine. Similarly, what will be the VID mean? It will be minus under root 2 VOV. So, what this range signifies? This signifies that in this range of VID, the current is steered from the Q1 transistor to the Q2 transistor. So, the point is that if VID is increased beyond under root 2 VOV, then ID1 remains equal to I, VGS1 remains equal to Vt plus under root 2 VOV, that we have seen from the expression. Then in that case Q2 will be off and the complete current will be steered through the Q1 transistor. Similarly, for the negative direction side. So, the range of VID, it is minus under root 2 VOV to plus under root 2 VOV. VOV is the overdrive voltage, that is VGS minus Vt. Next one is a small signal operation of MOS differential pair. So, we are going to do the small signal analysis of this differential amplifier. Small signal analysis means we will remove the DC sources, and we are doing it just to calculate the like output resistance, gain, etc. fine. So, in this differential amplifier, the input signal VID is applied in a complementary manner or balanced manner, such that VG1 is increased by VID by 2 and VG2 is decreased by VID by 2, fine. So, this VCM is the common mode DC voltage, right. This is the structure of differential amplifier. Here we are applying VID by 2 and minus VID by 2 at both the gate of Q1 and Q2 transistor. We can apply the single ended input also. This is differential input, right, because we are applying the input signal at the gate of both the transistors. In the single ended input, what happens? We apply the complete signal at the gate of the Q1 transistor, and the another for another transistor the gate is grounded, right. Now, see, after performing the small signal analysis, this is the resultant circuit. Now, the DC sources are removed, your DC voltage source, DC common mode voltage is removed. So, at the gate of Q1 this is plus VID by 2, at the gate of Q2 this is minus VID by 2, fine. So, what will be the drain current here? Drain current flowing through Q1 transistor, it will be the transconductance of Q1 transistor into the gate to source voltage, that is your VID by 2. Similarly, we can calculate it for Q2 transistor also. Now, what is the transconductance? The transconductance is the total current I upon VOV. I is the current source value and this I is equal to 2 ID, because ID is flowing through Q1 transistor, another ID is flowing through Q2 transistor. So, the total current is I. So, the transconductance is I upon VOV, and from the circuit we can see that the output voltage of Q1 transistor is minus GM VID by 2 into RD plus GM VID by 2 into RD, because we are applying the input signal in complementary manner. At one gate we are applying VID by 2, another gate minus VID by 2. That is why we are getting VO1 and VO2 positive and negative. Now, from here there is an important thing. We can take the output in the differential manner, we can take the output in the single ended manner. So, the circuit which I have described here, this is your differential output, because we are taking the output in between the drain of the Q1 and Q2 transistor. So, what is the advantage of taking the differential output in comparison with single ended output, that we can see here? The first case is if the output is taken single ended fashion. Single ended fashion means if we are taking the output from the drain of either Q1 transistor or Q2 transistor, only one of them, either Q1 or Q2, then in that case V1 upon VID it will be minus 1 by 2 GMRD, VO2 upon VID it will be 1 by 2 GMRD. Now, if the output is taken differentially, that we had taken, if we are taking the output between the drain of the Q1 and Q2 transistor, that is called differential output. Second case, then the gain will be VO2 minus VO1 upon VID. Why VO2 minus VO1? Because we are taking the differential output and we know the value of VO2 and VO1. Just put the value of VO2 and VO1, we will get GM into RD. Now, just compare that. in which case we are getting more gain. We are getting more gain when we are taking the differential output. So, in case of differential output we are getting double gain. In single ended output we are getting half of the gain, but in many applications we require single ended output. So, we need to convert that differential output into single ended output, but of course, there is advantage of differential output, that is the gain is higher. Now, the next one is the common mode gain and common mode rejection ratio. Now, for the same circuit we are going to calculate the common mode gain and common mode rejection ratio. Common mode signal is your noise signal or interference signal. Now, this RSS is the source degeneration resistance, and at the gate of Q1 and Q2 what is applied? VCM plus VICM. VCM is the input common mode voltage, common mode DC voltage in fact. This capital V, capital C, capital M is the common mode DC voltage, and the small noise signal or interference signal, that is VICM, right. So, what will be the current flowing through RSS? It will be 2I, because the I current, if I current is flowing through Q1 transistor, I current is flowing through Q2 transistor, then the 2I current will flow through RSS, that is the source degeneration resistance. Now, to calculate the common mode gain, again we will do the small signal analysis, just remove the DC sources, and after removing the DC sources and just convert that circuit into two half, one half and another half. This is your one half, this is another half, right. So, what will be the value of RSS here? Obviously 2 RSS, because if we are breaking that circuit into two parts, then half current will flow, corresponding to that the source degeneration resistance will be 2 RSS in both cases. So, here if we calculate the value of VO1 upon VICM, it will be minus RD upon 2 RSS, VO2 upon VID. This is your differential gain, that is 1 by 2 GMRD. Now, just see to it, this 1 by 2 GMRD, let us say it is equation 2, this is equation 1, 1 by 2 GMRD, this is the differential gain AD. It is corresponding to single ended output, it is corresponding to single ended output 1 by 2 GMRD. For differential output, the differential gain is GM into RD, but for single ended output the differential gain is 1 by 2 GM into RD, and for single ended output the common mode gain is minus RD upon 2 RSS. This is your common mode gain. What is common mode gain? Output upon input, output voltage upon input common mode signal, that is your common mode gain. So, from here we can calculate the value of CMRR, common mode rejection ratio, that is AD upon ACM. So, if we calculate AD upon ACM from equation 1 and equation 2, we will get GM into RSS, because RD by 2 it will cancel out. So, the CMRR is GM into RSS. So, this is the value of CMRR for single ended output, but if we are considering the differential output, then what will be the CMRR? If we are considering the differential output, what is differential output? Differential output means we are taking the output between the drains of two transistors. So, in this case we have already calculated the differential mode gain, that is GM into RD, and what will be the common mode gain in differential output? It will be VO2 minus VO1 upon VICM, because we are taking the differential output, that is why VO2 minus VO1, and in case of differential output this VO2 minus VO1 will be 0. So, ACM will be 0, that I have explained at the starting of this class when I had explained the operation of the differential pair in common mode, right. So, in that case we had seen that if Q1 and Q2 transistor in saturation region both are matched transistors, in that case whatever noise signal, whatever common mode signal is applied at the input, the output will be 0 if we are taking the differential output. So, ACM is 0. So, what will be CMRR? CMRR will be AD upon ACM, that is AD is GM into RD upon 0, that is infinite. So, the point is that when we take differential output, then CMRR is infinite, but of course, for ideal case, but practically it will be very high. So, we want the CMRR to be high. If CMRR is high, it means that the common mode signal is getting rejected in a better way. right. That is a good thing, right. So, for differential output, the differential gain is higher, CMRR is higher, but for single ended output, the CMRR is GM into RSS. So, in this class I have discussed the basics of differential amplifier, then I have discussed about differential output and single ended output. The advantage of differential output is higher gain and higher CMRR. We have also calculated the value of differential mode gain, common mode gain and CMRR for single ended output and differential output. So, whatever I have discussed in this class, this is for passive load. The next one is the active load. Now, we will replace that resistor with current mirror in the next class. This is the reference. Thank you.